Chapter 12, Elementary Chemical Kinetics, Section 12.6, Potential Energy Surfaces. A potential energy surface describes the potential energy of a molecule as a function of the relative positions of the atoms. One example is the potential energy of butane versus the carbon-carbon-carbon dihedral angle of butane. So we can look at this molecule from this direction, and you can see we can rotate the single bond between carbon 2 and carbon 3 to have different dihedral angles ranging from 0 to 360. And between 0 and 360, we have different conformations. So over here, we have this 4 carbon atoms on the same plane. It's called sine periplanar. And over here, we have a 60 degrees dihedral angle for this carbon 1, carbon 2, carbon 3, carbon 4. Alright, this dihedral angle. And here we have the so-called eclipsed conformation. We have this HCH3 and this H with the same angle. And due to the repulsion, we have higher energy here. And then now here we have this so-called anti-periplanar conformation. The two CH3 groups are opposite to each other. And now we have another eclipsed conformation with higher energy, lower energy, alright, and this is called gauche conformation. Finally, we get back to the 0 degrees or 360 degrees. So you can see there's a repulsion between these two methyl groups. There's a repulsion, smaller repulsion between these two hydrogen atoms and between these two hydrogen atoms. This is called sine periplanar versus this anti-periplanar. And also we have gauche conformation with lower energy and eclipsed conformation with higher energy. So this is the potential energy surface of butane with the dihedral angle of carbon 1, 2, 1, 2, 3, 4 as the horizontal axis. Here's another example of potential energy surfaces. Let's look at a reaction from A plus BC to AB plus C. So in the reactant structure, we have a BC bond. A is far away from B and C. And on the product side, we have the AB bond, and then C is far away from AB. So now let's look at a graph over here. This is a two-dimensional contour plot of the potential energy surface. So I want to look at this green dot over here. This is actually the transition state. The transition state for this chemical reaction. In this transition state, we have partially formed AB bond and partially broken BC bond. So this is over here, and right here, you can see we have a smaller BC bond distance, right? So this is the bond distance of BC. We have a smaller BC bond distance. Over here we have a larger BC distance. So right here at this point we have a BC bond. We have a BC bond with a short distance between B and C. And A is far away, so AB is pretty high. Okay, our AB is pretty large. And then you can go through this minimum energy path or intrinsic reaction coordinates. We go to this side. At this point, AB is short. Okay, AB is short. There's a AB bond. And then how about BC? BC is large. So the BC bond is completely broken here. We have AB bond. So this reaction can be described by this green curve that passes through the transition state, denoted by this green dot. A more specific example of A plus BC to AB plus C is the SN2 reaction between chloride and bromomethane in water. So on the left hand side we have chloride, and in this molecule we have a carbon bromine bond. On the product side we have a carbon chlorine bond, and we have a separate bromide in water. It's a typical SN2 reaction. We can also create the potential energy surface this way with the potential energy versus the so-called intrinsic reaction coordinate. And this intrinsic reaction coordinate includes the changes in the carbon-bromine bond distance and carbon-chlorine bond distance. In addition, this intrinsic reaction coordinates include the changes of the coordinates of these three hydrogen atoms relative to carbon. So you can see this is almost planar. This CH3 is almost planar. Over here it's definitely non-planar. On the product side it's non-planar. In the middle it's planar. So the intrinsic reaction coordinates just describe the changes of the coordinates of the entire molecule. And now you can see on the left hand side we have chloride and bromomethane. On the right side we have bromide and chloromethane. In the middle we have the transition state structure. So using a computational chemistry program, we can compute first the transition state and then do a intrinsic reaction coordinate calculation. We'll get some other structures along this minimum energy path to the left and also the minimum energy path to the right. And now we know more about this entire reaction path, not just the reactant, not just the product, not just the transition state, but some intermediate structures in between.